So, did it match up? This was a no-go. This was the right one, I hope. So what was the question really asking? It's saying we know these conditions. Acidic water in the presence of an alkene is going to give one carbon an H, the other carbon an OH. When the alkene's asymmetric, which one gets which? That question I just said out loud, which carbon gets which, is a regioselectivity question. So what I'm going to do is define that first and we'll prove how this is regioselective. So regioselectivity is a preference for one constitutional isomer over another. So when a reaction prefers to form one constitutional isomer over another possible one, that reaction is said to be regioselective. So clearly this is regioselective. If we put that into words, what do I mean by one constitutional isomer? I mean the OH is literally on a different carbon in our two possible answers. So if we put that into words, we said how do we specifically describe the regioselectivity of this reaction? We would say, well, look at that OH. It went on the carbon that is more substituted. So OH is added to the C of the alkene that is more substituted. So the OH went to the more substituted C. Let's look at that. So OH and H went on the less substituted carbon, right? Let's draw in what's on that other carbon. That other carbon already had an H. That H did nothing, but we did see that that carbon gained a second H. So H went where there's more H's. New group went where there's less H's. Why? The answer is always in the mechanism. Let's draw that out. So in order to start the mechanism, you need to know how to depict what's over the arrow, and remember that acidic water lies in the direction of equilibrium of forming hydronium. So we are going to draw that whole structure, not a condensed formula. We need the bonds to show the curved arrows, right? That's our acid. Who's going to act as our base or nucleophile? The pi bond. We lose the pi bond. See how that happens? It's gone. So we use it to attack and we use those electrons to make a bond to that new H we're going to grab. I'm going to circle this in green because remember we're tracking our H's. So that explains that H right there. New H goes on a carbon, one of the two carbons of the alkene. You know it's this one because I gave you the answer. Why is it that one? Well, let's evaluate what happens if it goes here. If it goes here, because these two carbons are sharing those pi bond electrons. They don't get to share them anymore because the pi bond is breaking. As it's breaking, one of the two carbons keeps those electrons to share with the H. So if this carbon keeps those electrons to share with this H, then we have no carbocation here. This is a full octet. This one will make a carbocation. That looks like a nice carbocation, right? It's tertiary, whereas this would be secondary. So that is the reason we see the regioselectivity. If we allow the less substituted carbon to be the one that keeps the electrons, we avoid a less stable carbocation. So we wouldn't want one here. This would be secondary. Now we get a tertiary carbocation. So tertiary carbocation. Stop. We have a carbocation. Should we rearrange? Nope, not really possible here, right? It's tertiary. There's no opportunity for resonance or ring expansion, contraction that would be favorable. So we keep going. Other two fates of a carbocation are to eliminate to form a pi bond. Well, guess what that would do? That would go backward. So it's time for it to do this other fate. Carbocations capture a nucleophile. Who could be our nucleophile? Well, what are we missing to get home? We need the OH. Water. Water is going to be our nucleophile. Not H3O+. That's not nucleophilic. That's an acid. Use the water because it has that lone pair ready to attack. And attack that carbocation. Now that shows why we get the OH on the more substituted carbon, right? Because that is the carbon that had to be the carbocation. So we want the more substituted carbocation. Stability from hydroconjugation. But in terms of thoroughness, we'll finish this whole mechanism. Now notice what bonded here, OH. It looks like I drew it up here, so I'll just keep it there, but it doesn't matter. Water attacked, and everything with it. You don't just get to separate off the OH or the O yet. You have to show the mechanism of how it turns into the OH. So notice this lone pair that was here was used for bonding. It's now here, right? So we have an oxonium ion, 3 bonds to oxygen. That's a common intermediate when water's involved or making an alcohol of any sort. So we just have to, no big deal, we just have to neutralize. We've done lots of acid-base proton transfer reactions. That's what we're doing next. Who could be our base? Well, water, of course. And now we're home free. So yes, the mechanism helps a lot, but it took a while to draw the mechanism. And sometimes we'll be looking at these reactions over and over and over again. And we'll want to kind of recognize that regioselectivity when it comes our way. A famous scientist, Vladimir Markovnikov, recognized that as well. So Vladimir Markovnikov, this dates back to 1800s, famous Russian scientist. He elucidated what he's calling what we now call the Markovnikov rule. And so it's defined for you here, so you don't have to write it down. Let me get this. There we go. In an addition reaction, this is how it was originally stated. Of a protic acid HX to an alkene or alkyne, the hydrogen atom of HX becomes bonded to the carbon atom that had the greatest number of hydrogen atoms in the starting alkene or alkyne. So, oh man, that's complicated, right? But it actually is meant to simplify. So let's see if we can summarize this a little bit more succinctly. Okay, so in other words, so I'm gonna keep him right there. The new group which is always the nucleophile, right? The one that attacked. It goes to the more substituted carbon, because if a reaction involves any sort of carbocation or carbocation-like character, then we prefer that to be happening on the more substituted carbon. Hence, the nucleophile is attracted to that because that's where the delta plus has built up, or the electron density has been removed. Substituted C. In other words, the H, if there is an H, goes to the carbon that is less substituted, or the carbon with more H's. Because what is a less substituted carbon? It's a carbon that has more H's. All right, so we will be classifying reactions and their regioselectivity. If we say, what's the regioselectivity? We might, instead of saying this big long phrase, well, the OH is added to the C of the alkene that is more substituted, we are going to say it follows Markovnikov's rule, right? Okay, so it's Markovnikov selectivity, right? If it does not follow Markovnikov's rule, we will occasionally say it's anti-Markovnikov, but we're not there yet, okay? All right, so just a little bit of interesting history, because some of this old-timey stuff is somewhat interesting. You learned recently about another Russian chemist, Zaitsev, who established Zaitsev's rule, which has to do with alkenes, right? When you form an alkene, you're doing the opposite. Instead of losing the alkene in addition reaction, you're forming an alkene in elimination reaction. We always like to form the more substituted alkene possible. And you think, oh, they both worked on alkenes. They're from a similar region. They're contemporaries, same time period, probably friends, right? That doesn't always make a mix for friends. Sometimes it actually makes a mix for enemies. So Zaitsev, bring him back. And I've had friends and students let me know Zaitsev basically means is a word that could be used for hare or bunny. Turns out Markovnikov can mean little carrot. And I was reading this text, Early Russian Organic Chemists and Their Legacy. So I'll just highlight this one thing out of interest while, yeah, it might actually be worthy of that little emoji there. University second choice of Markovnikov's junior colleague was Alexander Mykolovich Zaitsev. And so you can see the time period there, late 1800s again, while Zaitsev, a counterpoint to Markovnikov from the university's point of view, may have provided a counterpoint from the university point of view. They did not like each other at all. And in fact, they carried on a lifelong feud. So this comes from Early Russian Organic Chemists and Their Legacy, in the Springer book if you wanted to read more, but very interesting history there. They didn't like each other, so it's kind of appropriate that one means carrot, one means bunny, right? And the bunny can eat the carrot. So the carrot wouldn't be too fond of the bunny if it had feelings. But anyway, just thought I would bring that up since we're using these names so frequently. Maybe it'll help you kind of remember them at least. Another way I've seen textbooks rephrase Markovnikov's rule, because the original phrasing in the paper is a little more convoluted. We could say the new group goes to the more substituted carbon, the H goes to less substituted carbon. This is another popular phrasing. The nucleophile goes to carbon atoms with fewer hydrogen atoms. Fewer hydrogen means more substituted, right? While the proton goes to the carbon with more hydrogen. So you look at the two carbons, the one that has more H's gets the H, an extra H, gains the H. Let's get some practice doing that again. When we are considering regioselectivity, that is which carbon, constitutional isomers, that is not the same as stereoselectivity. So I promise we'd always ask that reaction too, or that question too. What is the stereoselectivity of a reaction? Like SN2, for example, inversion of the stereocenter, that was stereoselective. But I'm going to remind ourselves what that means here, because since we've defined regioselectivity, it's important to not mix them up. So remember that stereoselectivity is a preference for one stereoisomer over other possibilities or possible isomers. Okay, so because we actually did not make a carbocation here, and we made a carbocation. We did not have a back or front side attack exclusively. We had a carbocation, which means it could attack from either side. We also don't have a stereocenter here when we're done. So this particular reaction, we see no stereoselectivity. That means even if there was a stereocenter, we would get the likelihood of getting both enantiomers is equal. So none, no stereoselectivity, because a carbocation causes loss of stereoselectivity. It becomes planar, and then in a planar carbocation, it can attack from either side with equal likelihood, which means you get a 50-50 mix if it was indeed chiral. But since it did not make a chiral center, that's not even a question there. We will sometimes make some chiral centers where there was none. So let me show you an example here in this margin. I'm just going to make a generic one before we move on to our real example. Here's an alkene, a tri-substituted alkene. I'm going to put an R1, an R2, and R3 on there. Let's do addition of water. Now, we know from Markovnikov's rule, R1, R2, We're going to lose the pi bond when we do an addition of water. So the pi bond's gone. One carbon gets the H, one carbon gets the OH. Pause and think for a minute. A and B. Does A get the OH or B get the OH? I gave A the OH, right? Markovnikov's rule. B got the new H. That's not all that happened. Do we have a stereocenter here? Do we have a tetrahedral carbon, I should ask, that we have to designate RS to? No, but here we do, right? If R1 does not equal R2, and it doesn't equal this thing, if these are all unique, then yes, we've generated a stereocenter. So when a compound is previously not chiral, but upon adding a reagent, we get a new stereocenter. We call that prochiral. Okay, so this is prochiral. Pro, you might remember that prefix from some other things like prologue, prototype, meaning the Greek prefix for like before or prior to. So it's not chiral at the moment, but this is a prochiral alkene. That means watch out. You do an addition reaction, you lose the pi bond, you now have a chiral molecule, right? So you have a chiral tetrahedral center. My cat liked that comment on prochirality, so I think I'm going to let him join us. Okay, may we resume? Thank you, Buckminster Fullerene. I know. All right, so now I'm going to be using this phrase too. So we watch out for stereochemistry, because after addressing, wow, okay, here's a box. Maybe this will help. Stereochemistry, we're getting ready for that. So we're going to be talking about, do we form enantiomers? Do we form diastereomers? Do we form selectively one versus the other in terms of which enantiomer? Do we form even a chiral molecule at all? In other words, we answer that question by looking at the alkene. Is the alkene prochiral? Can it generate a chiral molecule upon losing its pi bond? Sometimes it's something you can't always predict so quickly, because we might say, hey, I know I need to get a racemic mixture, and I know that I'm going to do Markovnikov's rule, so I'm just going to be done by predicting this product right here. So here's the folly in that, right? So here's where we get to bigger, more complex molecules, and you say, well, I know this now. This is simple. I don't need a mechanism. Mechanisms weigh me down. They're too much work. I'm just going to guess based on the rules. Lose the pi bond, more substituted carbon gets the new group. Remember, this is adding H and OH, so this gets the OH because it's the more substituted carbon. This gets the H, and I'm done. Turns out that's wrong. So yes, that reasoning helps talk you through it. Why is this wrong? I'm going to show you the right answer. So redraw the framework. I've got the OH over here, and I've got an H over here. And my methyl is still there. I'll even draw the methyl. So look at that. I'll draw my two H's just so we can track them. So my H and OH that I predicted here did not end up there. Yes, the H did. But what happened to the OH? It's actually not on either carbon that was part of the alkene. It's way over here now. What could explain that? Well, the mechanism is going to help. But when that happens, when you see that we added across a pi bond, so the pi bond's gone, however, the two new groups are not adjacent to each other like they would have been on the carbons of the original carbons of the pi bond, that's a hint that there was a rearrangement during the mechanism, which is why you always need to write out the mechanism. And the more you do it now, the faster you'll be at it later, like test time, right? So let's do this. So remember, this collectively is our H3O plus. Now we're going to, the first step's the same. So draw out your benzene ring right there, attached to what is not a benzene ring, a cyclohexene that is now a cyclohexane with a positive charge. So where is that positive charge? Of the two carbons, the better positive charge would be residing on that tertiary carbon. So that's where I'm going to put it, which means it did not get the H. It means that the other carbon that was less substituted, that had an H already to begin with, gets the second H. So I like to track these things just because it helps me remember where everything came from and how the mechanism worked, right? So here's our carbocation intermediate. Now you always stop. It's carbocation. Before you do the next step, can it rearrange? Well, it is tertiary. What's better than tertiary? Tertiary with resonance. And we got to watch out because we have pi bonds nearby. So if I actually can manage to get it over here, which I know my answer had it here, that means I must have had the carbocation here. And if I manage to get it over here, it will not only be tertiary, it'll be tertiary with resonance. So how can I make that happen? I see an H there that's not drawn in. We do a 1,2 hydride shift. We pluck that H in its bond out, move it over. We leave an open octet behind, right? 1,2 hydride shift. And there we go. There's our benzene ring. Now, adjacent to the cyclohexane carbocation that has moved its carbocation over there, because this H, if you want to color code it, is now over here. The other new H in green is here. Okay, now we are tertiary carbocation with resonance. That's about as good as it can get. We may proceed. Not only that, when you are faced with a mechanism problem in which you are trying to prove the formation of one product over another, like this one, we know what the answer is. We know the OH is going to go there. So we can only have it go there if it got to be attacked there. It can only attack there if there's a carbocation there. So that's what we facilitated with that maneuver. All right, now, other fates. We've already dealt with rearrangement. We're not going to eliminate. We're going to capture a nucleophile. Nucleophile is water. Let water attack. It can attack from above or below, right? So we can get a plus, a wedge, or a dash on there. But I'm not going to even draw that right now. I'm just going to draw the O, because that's just too many different things to draw while I'm working out which regio isomer we have. So H and H and H. If you want to keep tracking them, that was the blue H that moved in the hydride shift. That was our new green H. This is our new OH that we're going to get in the end. We have to get rid of that stray H right here that's making that an oxonium ion. So that means just bring in the water to help do our simple neutralization step. deprotonate, in other words. Take that H off, leave the electrons behind. If you didn't draw in your lone pair, you might want to, just to kind of clarify where that's all coming from. Okay, so what we want to think about here also is our final product right here. How many stereoisomers did we form? Well, this is a stereocenter, and it used to not be one. Actually, it always was one, sorry. So that is a stereocenter. The one that used to not be one, because the alkene was over here. This is now a tetrahedral stereocenter. So that means we have all the, because these were both carbocations at one point, we have the dash and the wedge product for the methyl. We have the dash and the wedge OH. So we have all possible stereoisomers. So we have the 4. This is a mixture of the 4 stereoisomers there, okay? I'm just acknowledging that with the stereocenter, but if we were to draw them all out, which we will in another exercise, the point of this one was to look at the rearrangements and remind ourselves of that, but I'm just alluding to that here because we are going to ask in the next exercise to draw all of them, okay? All right. So like I said here, I wanted to really focus on, at the moment, that we watch out for carbocation rearrangements, right? And then it's never going to do eliminate to form a pi bond because that would take us backward to the alkene. So the other fate is the capturing the nucleophile. So that's the essence of the mechanism, right? We form a carbocation, we stop, we evaluate if we should rearrange. We move on once we assess that situation, then we capture our nucleophile, clean it up if we have to, because it didn't, you know, that proton transfer oxonium ion scenario. And then voila, we have our groups added across the pi bond. Now we're going to focus on stereochemistry a little bit more, which is what you have to watch the instructions. Predict all of the products. So let's draw every, be explicit. Draw every stereoisomer. We're not just going to label, oh yeah, that's chiral. We know what that means. Because the reality is we learned that recently, but it doesn't help. We could forget it, right? We need to actually draw them out sometimes to remind ourselves. Draw every stereoisomer to really get what that means. So watch that on your prompts and homework and exams when it says draw out every single product or indicate racemic with a plus or minus. All these different instructions telling you how to draw out the stereoisomers. So in this scenario, draw out every stereoisomer. That means we're going to draw out every stereoisomer. If there's 5, we're going to draw all 5. If there's 4, we're going to draw all 4. Okay? All right, so we learned our lesson that it helps to draw a mechanism, and it says to draw it anyway. Another thing to watch out for is, uh-oh, that's not water over the arrow. That's alcohol. Well, what does that mean? I'm going to put a star here. Can add ROH as well as HOH. You can add alcohol as well as water. What does that mean? That means one carbon gets the H, the other one gets the OR. All right. So the best way to kind of think about that is to remember that these two things together, sulfuric acid and methanol, or any alcohol, ethanol, other alcohols, the equilibrium would favor the protonated alcohol. So just like it favors the protonated water, instead we have our R group here, Me. This is our dominant acid now. We use that in the mechanism. The pi bond takes that H. This is just like before. It's just one H is replaced with an R group. So this mechanism has a very small change, But it's a big deal because we use alcohols a lot. So you want to make sure you're comfortable with that. I'm going to abbreviate that as methyl. All right, now, as soon as you break that pi bond, you got to think, where's my better carbocation? Yes, it is better right there, tertiary. Should we rearrange? There's no opportunity for resonance and it's tertiary, so don't need to do that. Let's keep going on to capture a nucleophile. Who's our nucleophile? It's been water over and over again. Am I going to use water? No, because water is not present. Look over the arrow. Which is a better nucleophile, methanol or sulfuric acid? Definitely methanol, right? So now the lone pair of electrons attacks the carbocation, and wait, the carbocation is flat and planar, which indicates that the methanol could have equally attacked from the bottom as it could have from the top as well as the bottom. So 50-50. That means we have the methanol coming in from the wedge location as well as the dash location. And the answer said to draw everything. But I'm still going to wait till the end. I'm just going to make a little note to remind myself. Because otherwise your mechanisms get huge with lots and lots of structures. The goal of the mechanism is at first to get the regioisomer correct, all the bonds in the correct place, while noting stereochemistry, right? So methyl is here, the O and everything attached to it, so including that methyl and the OH. We now have our protonated oxygen that needs to be neutralized. But wait, the whole point of that carbocation discussion was to acknowledge that I am making a stereocenter here. So I'm marking it in a color so that I don't forget to go back to that. Okay, so now we have our neutralization step. Who's going to neutralize? You didn't say water, did you? Got so used to doing that. Water's not there. You can't throw it in. It would be wrong. Methanol's there. A lot of these methanol. Okay, so now we have this OMe, and I have my stereocenter marked. Okay. So, draw every stereoisomer. Did I do that? No. This stereocenter right here did not participate in the reaction. It remains unchanged. It's always a wedged methyl. However, I could have had a wedged methyl and a dashed O methyl, or I could have had, and you maintain the wedge over here, a wedged O methyl and a dashed methyl. What is their relationship? Well, because I have a stereocenter that stays fixed, let's say it was R. R, R. These two are opposite, right? One of them is S and one's R. So I'd have an RR and an RS. I just described diastereomers, didn't I? So it's not always racemic unless you only have the one stereocenter that was formed. If you had a pre-existing one, then you formed a set of diastereomers. That's hard, right? That's hard. Do we always form diastereomers? No, we can sometimes form racemic mixtures. Do we always form a racemic mixture? No, you got to work it out. You still have to think through that. I'm going to pause here because that is tough. I actually recommend getting out a blank page right now and trying to redo this one more time because it threw in alcohols adding across a pi bond. Regiochemistry was part of the discussion, the mechanism, and stereoselectivity, and to convince yourself that diastereomers formed. Come back and we will move on to adding another group across the pi bond.